Let's now consider the Dirichlet problem. We recall that it took the following form. We are going to find U, which is called the solution, and this is an element of W0 such that A of U phi is equal to L of phi for every phi in this space. And we remember that the definition of this bilinear linear form is given by this integral, and the linear form or functional, if you like, L of phi is given by this integral. Let us now discuss something else for a short moment. If we have some real function called, for example, f of x, then the minimum of this function over some space, for example, if we take this set, or which is in this case an interval, the green interval from this point to this point, and we consider the minimum of this function in this interval, then we will find that the minimum is at this point x0. Here is the minimum. If we use another interval which is maybe a little bit shorter from this point to this point, then we will have the minimum on this point. Here will the minimum take place. So one way of writing this is that f of x0, which is the value of f of x in, for example, this point, is, and we give this, we write it in this way: the minimum taken over the set k for all x element in this set k of the function f of x. So this is the way of writing that the minimum value is f of x0. Another way of writing this is the following: find x0 element in this set k. In this example, the interval k is this green interval, such that f of x0 is less than f of x for all x in this set k. So let's keep this in mind when we are discussing or continuing with the equivalent minimum formulation of the problem which we now have described above. I mean, this double star problem. So this is one way of defining the Dirichlet problem. Another way is an equivalent minimization problem. So it's called a minimum formulation of this problem, double star. And this formulation is as follows: find U in W0 such that, and we call this triple star, such that f of U is less than f of phi for all phi element in W0, where this capital F of phi is equal to half A of phi minus L of phi. So this is called a minimum formulation. It's also called minimum energy formulation, because it turns out that this f of phi can be interpreted as the corresponding energy the energy corresponding to this temperature field. If the problem we are discussing is, for example, the Poisson problem for heat in the case where we are simulating heat distribution. So here is the exact solution, and the minimum formulation is in some sense more natural from a physical point of view. It's easier to understand because nature is often like this, that it chooses a temperature field such that the energy is minimized. We are now going to give you a short proof of the equivalence between these two formulations, double star and triple star. So this we can use these formulations both ways. The equivalence is we are going to prove this equivalence, and in order to prove equivalence we have to prove this implication and the other implication. So let's start with this implication. That is, we assume that double star is the formulation that U is described, that we have found some U which have the property that A of U phi is equal to L of phi for all phi element in W0. We will also note that A of any function W will always be strictly positive, and it's possibly positive due to this. You remember the definition of this bilinear form. It was given by this integral, and now we have W on both places here. And this is this multiplying the gradient, or multiplying any vector with itself gives the absolute value of this vector square. And since lambda is a positive, strictly positive function, which we always will assume in this course, it's rather obvious that this must be larger than 0, or equal to 0 if this gradient is 0. Okay, let's keep this in mind, because now we can replace this W, which is an arbitrary element in W0. We can replace this with any kind of function. For example, let W be equal to the solution U minus the arbitrary function phi. So then we know that this is true. This is always larger than 0. Now we utilize the property that this bilinear form in fact is linear in the second argument here. So then we obtain this. This is just the linearity in the second variable. And next we can utilize that this bilinear form also is linear in the first argument, and then we obtain this. And minus, we use exactly the same argument that the bilinear form is linear in the first argument here, and we obtain this. Noting that from the definition of A of phi U, which is an integral, we note that it's arbitrary if we put A of phi U or A of U phi. That these quantities are identical. So this guy and this guy is equal. Therefore, we can put them together and we obtain this. And using that this larger than 0, we obtain that this must be larger than 0. Now we can divide both sides of this inequality by 2. It's not easy to understand at this moment why this is a good thing to do, but let's just do it. Then we obtain directly this inequality. Now I just put this. No, I put this on the other side of the inequality with changing the sign, and we obtain this inequality. Okay, now I go back, and you remember that we have already assumed double star. So we have assumed that A of phi u is indeed equal to L of phi for all phi. In particular, for phi equal to u. So therefore, A of u must be equal to L of u, and A of phi u must be equal to L of phi. This is just what we have assumed in double star. But now recall that the definition of f of phi, it's identically with this. Just go back and see what we have. Here is the definition of f of phi, so we know also that f of u must be equal to half A of u minus L of u. So therefore we obtain that this is f of phi and this is f of u. So now we have proved that f of phi is always larger than f of u. That means that this functional attained its minimum value for phi equal to u. So now we have proven the implication.